In this video, we're going to talk about the derivatives of secant and tangent. We might touch on cotangent and cosecant as well. But in order to do that, I want to reiterate some geometric intuition. And so in the last video, we talked about how the behavior of the arc length of a circle should approximate the behavior of the chord as we take the limit as that angle approaches zero. And the intuition here is that if you can imagine we're taking a smaller and smaller angle, these 2 points are going to get closer and closer together, these 2 points on the circle. And as that happens, you're going to get a smaller and smaller and smaller sector. And the behavior of this arc length here, as that happens, is going to be almost indistinguishable from a tangent line that approaches a circle here. It's going to be almost indistinguishable from the behavior of the chord. And the chord, of course, is just the line that connects the 2 points on the circle. So here, it's a little bit easier to see the difference. It would be this line here that connects those 2 points on the circle. But you can imagine that as this sector gets smaller and smaller and smaller, the behavior of this chord and this arc are going to be indistinguishable from one another. But in order to prove that, we had to find first a formula for the arc length. And you can imagine this is pretty easy to do. The ratio of the arc length to the total circumference of the circle, which is 2 pi r, should be equal to the ratio of the angle we're dealing with to the total angle measure of the circle, which is 2 pi. Multiplying both sides by 2 pi r here, we get that the arc length is equal to r times d theta. That's simple enough. But what about the chord? So you can imagine if we connect these 2 points on the circle here, we're going to have this isosceles triangle here. It's the same thing. This diagram is the same thing as this one. It's just drawn a little bit bigger, so it'll be easier to work with. And so dealing with this isosceles triangle here with an angle of d theta, it's actually pretty simple. We just drop an altitude here, which I've indicated with this dotted line. Each of these angles is going to be d theta over 2. This altitude is going to bisect it. And then sine of this angle, sine of d theta over 2, is going to equal half of the length of the base, so x over 2, divided by the length of the hypotenuse. That's just opposite over hypotenuse. So divided by r. Now we can solve for x, which is the length of this base, pretty simply, just by multiplying both sides by 2r. So we get that x is equal to 2r sine d theta over 2. And we're intuiting that the behavior of this arc is going to be indistinguishable from the behavior of the length of this chord or the base of an isosceles triangle as we take the limit of this d theta as it tends towards 0. And so in order to prove that, we took the limit of as d theta approaches 0 of the ratio of the length of the chord or the length of the base of an isosceles triangle with an angle of d theta. We took the limit as d theta approaches 0 of the ratio of the length of this base to the arc length of the circle. And what we found is that these r's canceled, and if we divided both the numerator and the denominator by 2, this was equal to the limit as d theta tended towards 0 of sine d theta over 2 divided by d theta over 2. And this is exactly the same as taking the limit as theta approaches 0 of sine of theta over theta. A division by 2 here is going to be negligible because we're taking the limit as this variable approaches 0 anyway. And this is one of our special trig limits that we went over in the squeeze theorem video. It comes up all the time in calculus. This is just going to be equal to 1, which means that we are correct with our intuition. The behavior of this arc length is going to approximate that of the chord, but it's also safe to say that the behavior of an isosceles triangle will approximate that of the arc length as this angle tends towards 0. And so the length of the base of this isosceles triangle is going to be equal to r d theta for d theta sufficiently close to 0. Very infinitesimal lengths or angle measures for d theta. And this is going to be the intuition that we want to build because for our proof for secant and tangent, we're just going to rely on triangles themselves, and we're actually not going to look at the unit circle. Right, so using these ideas, we can actually construct a diagram that lets us figure out what the derivatives of secant and tangent are. And so I've constructed this right triangle here with an angle of theta and a base length of 1. And if this is a base length of 1, then this is our angle theta. Then we could say that tangent of theta is going to be equal to the length of this opposite side, divided by the length of the base, or the adjacent side, which is just the length of the opposite side divided by 1. So the length of this opposite side here must be equal to tangent theta. So this is going to be equal to tangent theta. Similarly, we could say that cosine of theta is equal to the length of this adjacent side, which in this case is just 1, divided by the length of the hypotenuse. And if we solve for the length of the hypotenuse, we get that that's just equal to 1 over cosine, which is equal to secant theta. So we have that our hypotenuse here is equal to secant of theta, and our opposite side here is equal to tangent theta. And so here I've constructed a isosceles triangle on top of this right triangle with a very small angle d theta that is to represent a very small change in the angle theta. And because of what we just figured out, we can now understand that the length of this side right here is going to equal secant theta for the length of this r value here, essentially, multiplied by d theta. That's going to be the length of this side here. And that doesn't really fit here, so I'm just going to write it off to the side. Length of this side here is going to equal secant theta d theta. Okay, and you could think that if I was to hypothetically extend this out to where this triangle would sit if we were drawing from the base, as if these weren't two separate triangles, but that we were dealing with a full triangle that had an angle here of theta d plus d theta, theta plus d theta. Then what would these full sides represent? Well, this would represent, this whole side here would then represent secant of theta plus d theta. And so what I would say is that this dotted segment here would represent the change in secant theta as a result of changing our theta measure. And similarly, the length of this dotted line segment would represent the change in tangent theta as a result of changing our angle. And what's also safe to say is if we're taking the limit as this d theta approaches 0, not only will this isosceles triangle fulfill these properties, that the length of this is going to be equal to the length of this side multiplied by the value of this angle, but also these angles here are going to approach 90 degrees, because as we make this angle smaller and smaller and smaller and smaller, these two angles, which are equal, must get bigger and bigger and bigger, closer and closer and closer to 90, such that the total interior angle measure of this triangle maintains that 180 degrees. And if this is equal to 90 degrees, I would also add that this angle must be equal to 90 minus theta, 90 minus theta because this is theta and this is a 90 degree angle, so this must be equal to 90 minus theta for all of these angles to add to 180. All of these angles must also add to 180 because we're dealing with the straight line here. 90 minus theta plus this 90 degree angle plus this one must equal 180, so this angle must also equal theta. And with that information, we know that we're dealing with a similar triangle here and with our original triangle. These two triangles are similar triangles. And with that, we can construct some ratios and we can solve for these derivatives. And so if I draw these triangles next to each other, maybe in a different color, we have our original triangle here. This is going to be angle theta. This is 90 degrees. This is a side length of 1, tangent theta, and secant theta. And if I draw our new triangle here, the dotted one, and I line it up such that the angles are in the same position, this would become the angle theta. Our hypotenuse here is going to be the change in tangent theta, and our opposite side here is going to represent the change in secant theta, and then this side is represented by secant theta, or is equal to secant theta multiplied by d theta. And now I have all the information I need in order to take some derivatives, because what we are interested in for the derivative of tangent theta, for example, would be the ratio of a very small change in tangent of theta as a result of the very small change in theta. And so all we need to do is divide these two sides and see what that's equal to here. And so if we do that, we would get that the change in tangent theta divided by secant theta change in theta would be equal to secant theta divided by 1, which is just secant theta. And if we multiply both sides by secant theta, we see that a very small change in tangent theta as a result of changing theta, a very small amount, an infinitesimal amount, otherwise known as the derivative of tangent theta with respect to theta, this is going to be equal to secant squared theta. And similarly, if we take a change in secant theta, we take the ratio of that to this length of this triangle here, we get secant theta multiplied by a very small change in theta. This is going to be equal to tangent theta divided by 1. Tangent theta divided by 1 is just tangent theta. And so a very, very, very infinitesimal change in secant theta as a result of a very, very, very infinitesimal change in theta, otherwise known as the derivative of secant theta with respect to theta, this is going to be equal to tangent theta times secant theta. And so this is a very quick geometric way in order to solve for the derivatives of tangent theta and secant theta. But I want to point out here that this is not our only option here. And if we wanted to circumvent this entire process of thinking of what diagram to draw, drawing it out, finding all these ratios, and looking for these similar triangles in an effort to calculate a derivative, what we could do is we actually already have all the tools in our toolbox in order to solve for these derivatives without any of that hassle. And what I mean by that is, like, let's take for example, the chain rule. The chain rule. Secant theta is just equal to 1 over cosine, which is the same as cosine of theta to the power of -1. We know what the derivative of cosine of theta is. We know how to take the derivative of a function which is being raised to the power of -1. We could just use the chain rule. This is going to be equal to the derivative of the outside function applied to that inside function. So we'd get -1 over cosine squared of theta, which is the same as -secant squared theta. And then we multiply by the derivative of the inside. By the derivative of the inside, derivative of cosine of theta is just -sine of theta. These negatives would cancel, and we would get secant theta multiplied by sine of theta multiplied by secant theta, which is the same as dividing by cosine of theta. And then this whole expression is just equal to secant theta tangent theta. And similarly, we could also use the quotient rule in order to take the derivative of tangent theta. Tangent theta is just equal to sine of theta over cosine of theta. And if we're taking the derivative here, it would just be the derivative of the first times the second, which is just cosine squared theta minus the first times the derivative of the second. The first times the derivative of the second is sine of theta times -sine of theta, which is just -sine squared of theta. And so you would add these together, you get sine squared of theta, because that negative would multiply with this negative out front. And then we would be dividing by the second function squared. So that's going to be, we'd have a cosine squared theta in the denominator here. This right here is just our Pythagorean identity. You could think of on a unit circle. If you are to square cosine of theta and add it to sine of theta, that must equal the radius squared. The radius of that unit circle is equal to 1. And so when you add these two together, this is just equal to 1 over cosine squared theta. This is just equal to secant squared of theta. And so this is why we derive these rules for the quotient rule, for the chain rule, and other things, is because it allows us to circumvent all of this hassle that is necessary when you are attempting to divert to first principles in order to solve a problem. That's not to say that this is not important. Being able to do this is how we got to this place, or is how we got to the point where we were able to do this at all in the first place, because we had to derive the chain rule, we had to derive the quotient rule, but understanding these abstractions allows us to approach and negotiate these problems much more efficiently. So with that in mind, we can find the derivatives of our last two trig functions pretty simply. The derivative of cosecant theta with respect to theta is the same as the derivative of sine of theta to the power of -1, which is just going to be -1 over sine squared theta multiplied by cosine of theta. That's just the derivative of this outside function applied to the inner one multiplied by the derivative of that inside function. This is going to be negative cosine theta over sine theta, which is negative cotangent theta, multiplied by 1 over sine theta, which is cosecant of theta. So that's our derivative for cosecant. And our derivative for cotangent of theta with respect to theta is just going to be equal to the derivative of cosine theta divided by sine of theta, which is going to be the derivative of the top times the bottom, which is cosine theta times negative cosine theta, which is going to be negative cosine squared theta. And then we're going to subtract the top multiplied by the derivative of the bottom, which is going to be equal to sine of theta multiplied by sine of theta. So we're going to subtract sine squared theta. We're going to divide by the bottom squared, sine squared theta. This is going to be -1 times cosine squared theta plus sine squared theta divided by sine squared theta. And this goes to 1, and we're just getting -1 over sine squared theta, or negative cosecant squared of theta. That's our derivative for cotangent. Now that said, I would like to encourage everybody not to rely on the abstractions of the quotient rule and the product rule, the chain rule, and all that, but to try to prove these trigonometric limits geometrically from first principles. And you can do so for sine and cosine by simply setting the hypotenuse of that right triangle with an angle measure of theta equal to 1. We did something similar to this in the last video. We discussed a geometric proof for the derivative of sine and cosine, but it was a little bit different than this, not quite exactly the same. You could definitely do it with this isosceles triangle here with an angle measure of d theta. And similarly, you can definitely calculate the derivatives for cotangent and cosecant in a similar manner, just instead of setting the hypotenuse equal to 1, or like in the beginning of the video, the adjacent side equal to 1, you just set that opposite side equal to 1, and you can calculate the derivatives for cotangent and cosecant geometrically. So I encourage everybody to give these a shot and try to fill out these diagrams and see where those derivatives come from geometrically.